Hello everyone, my name is Sunit and I'm here to present my poster about the work I did at Physical Research Laboratory, Ahmedabad. It is about determining the ground state energy of atoms using the relational quantum eigensolver algorithm uh, with taking two ansatz into account, hardware efficient and unitary couple cluster ansatz. So as the plan of the work goes, we try to evaluate this expression for the ground state energy. So as you see this highlighted u theta, this is this part. So u theta can be chosen in multiple ways. We can take a unitary couple cluster ansatz that is theory motivated and a hardware revision ansatz. We here in this case we're taking R by RC that is convenience motivated in a way that it is recommended mostly by the quantum hardware. So the choice of systems we take for testing is some neutral atoms and ions. So we study the various factors that go into a typical VQA calculation, including mapping, basis, classical optimizer, and backend simulator. So we'll come to these later, what the things are. So these results we get are benchmarked with the classical methods like couple cluster and full configuration interaction, the best in a provided basis. So what the idea is, we have to calculate the ground state energy. So in order to solve the Schrodinger equation, what we do is we take approximate methods. So starting with Hartree-Fock method, and then we apply, take into account correlation effects and apply post-Hartree-Fock methods, usually called. There are many different methods available. So configuration interaction, couple custom method, etc. So here we try to calculate it using the VQ algorithm, which is a hybrid quantum classical algorithm. So part of it is computed on a classical computer and part on a quantum computer. So this part you can see here is a classical input which takes into account calculation of um, integral electron integrals, Hartree-Fock state, and then mapping is done on a classical computer as well. The measurement of the expectation value occurs on a quantum computer. So once the total energy is calculated, so it is fed into a classical optimizer where parameters theta is updated until a minimum ground state energy value is obtained. So we expect a different speed up from the VQ algorithm and it's the best choice in the NISQ era because it's based on the variational principle and hence the energy we obtain is variational. So coming to the factors we discussed earlier are important for VQA calculation. We see here if you want to simulate this following Hamiltonian, a sample toy Hamiltonian we can say, we need to evaluate these factors. In these coefficients. So these can be done on a classical computer. So you need to and we use for our work PySA driver for calculation of these. So later A dagger and A that is creation and addition operators are needed to be converted into XYZ gates using mapping. So this mapping can be of three types: Jordan-Wigner, parity, and Braviquet. So the now coming to the U theta, that is ansatz we take. Um, so it is based on classical coupled cluster method, which uses an exponential ansatz. So there's some virtual and occupied states. So it deals with basically the excitations, the single excitations as well as the double excitations. So if you see this expression here, the t exponent t is t1 plus t2 and so on. And you see this is the single and excitation, and this is the double excitation. So the unitary couple cluster is based on the same method, takes into account same excitations, except that it can be converted. It is unitary form because of T minus T dagger, where T is the excitation operator and T dagger is a de-excitation operator. It can be converted into a circuit form that can be implemented on a gate-based quantum computer. So next ansatz we take is the hardware revision ansatz. We take in this case R by RC. It is a layer of RY and RC rotation gates and connected. Each qubit is connected by a CZ entanglement. So here you see the circuit of the same. So coming to the results section, you see that we have evaluated different results for different mappings here. So if I zoom in a bit, you will see that here are the different methods of calculation. So this is the SCI energy, this is the Hartree-Fock energy, and this is the CCST energy. So after Hartree-Fock, electron correlations become important. So Here you see that UCCSD ansatz takes into account all the electron correlations, whereas the hardware efficient ansatz only uses the Hartree-Fock method and hence does not take into account the electron correlations. This is a zoomed in view of the same plot, uh, but this focuses more on the mappings, which mapping performs the best. So Jordan Brickner is best for S203G, whereas Bravicator is best for S26G, and same trend here follows for S26G. So you see here, next is the computation cost. You see the number of parameters very linearly with the increased number of qubits for RYRC insats, and it rises exponentially with uh, number of qubits and for UCCSD ansatz. Similar is the trend for gate operations. This is RYRC, the red curve, and these are the UCCSD curves, and you see the parity mapping is the most expensive among all the mappings we consider. So coming to the third plot in this figure, we see that the depth, with the increase in depth, the error always increases, and also the computational expense increases. So as a result, it is always recommended to use lower depths. For UCCSD, it can be said that the depth can be used 1 or 2, whereas for RYS, it's hard to predict which to use. So either that it should be below 10, but we have to see which gives the minima. Next is the optimizer dependence, and we see that the optimizer, we compare our conjugate gradient, Cobila, and LBFGSB, and we see that LBFGSB converges with lowest number of iterations and lowest error, whereas CIG oscillates a lot and takes more uh, iterations into account. Our Cobila converges smoothly but takes more error, converges to more error. Coming to the last plot, it says that the beryllium, it is a plot for beryllium atom taking entanglement strategies. So you see that the beryllium atom chooses the best entanglement strategy to be linear. That is, each qubit is connected to the next qubit. Others are like full entanglement, where each qubit is connected to each other qubit, and circular entanglement, which forms the ring strategy. SCA is given in this circuit template. So we conclude that there are different factors that go into the VQA calculation. Some factors contribute to the error more than others, and the circuit cost of RYRC is low, but it comes at the expense of accuracy, whereas the UCCSD answer is expected by theory to perform well in terms of accuracy, but computation cost is too high for the present quantum machines in the era. With this, I conclude. Thank you.